Hello, I welcome you all in today's lecture. In this lecture, we will discuss the design procedure for high strength friction grip bolts as per IS 800 2007. Now, in the case of high strength friction grip bolts, special techniques are used for tightening the nuts in order to induce a specified initial tension in the bolt, which causes sufficient friction between the connecting surfaces. So due to this friction between the connecting surfaces, the slip in the joint is eliminated, and hence the joints with high strength friction grip bolts are called as non-slip connections or friction type connections. You may also call them as slip critical connections. So the induced initial tension in the bolt is called as the proof load of the bolt. Now, as per clause 10.4 of IS 800 2007, the design shear strength of high strength friction grip bolt as governed by slip is given by VDSF, and that is VNSF by gamma MF. Basically, slip critical bolts are not cetosed in shear because the resistance is provided by the friction between the connecting plates. However, code provides design shear strengths. They are really design friction values on the connecting surfaces, so that the designer can handle the connections in just the same manner as are the bearing type connections handled. So it's actually design slip resistance of the bolt or design slip strength of the bolt. So we have design slip resistance of the bolt VNSF by gamma MF, where VNSF is nominal shear capacity of the bolt is governed by slip, and that is given by mu F multiplied by Ne multiplied by Kh multiplied by F0, where we have mu F as the coefficient of friction or slip factor and is specified in table 20 of IS 800, and Ne is number of effective interfaces offering friction resistance to slip. For example, in the case of a lathe joint, we have a friction grip bolt and we have only one surface, that is the interface between the two plates, which offers the frictional resistance to the load. But in the case of double cover butt joint, we have two interfaces that provide resistance to the applied load. That is, we have this interface at which frictional resistance is developed, and we have this face at which frictional resistance is developed. So Ne in this case is 2 and Ne in this case is 1. And we have value of Kh, that is a coefficient, and its value is 1 for the fasteners or bolts in standard clearance holes, and its value is 0.85 for fasteners in oversized or short slotted holes, and for fasteners in long slotted holes loaded perpendicular to the slot. So we have different types of holes for high strength friction grip bolts. It's the standard hole size, that is we have the clearance for the bolt hole as per the standard given in IS 800 2007, and we have this is the oversized hole, and this is actually the bolt shank, and this is the bolt hole. So the clearance is not as per the standard clearance, so we call it as oversized. And we have short slotted hole. In this case we have a provision for, rather a small provision for movement of the bolt, and this is long slotted hole, in which case we have the provision for large movement of the bolt. That's called as long slot. And we have value of KH as 0.7 for fasteners in long slotted holes loaded parallel to the slot. That is, if the load is applied, this is the bolt hole, and if the load is applied along this direction, that is the load is parallel to the slot, and if the load is applied in this direction, we say the load is perpendicular to the slot. And we have the value of gamma MF, that is partial safety factor for friction type bolts, and its value is given as 1.1 if slip resistance is designed at service loads. That is, if we are designing the joint on the basis of working load or service loads, that is the working stress method, and it is taken as 1.25 if slip resistance is designed at ultimate loads. That is, we actually multiply the service load by load factor and we call it as an ultimate load. And value of F0, that is proof load, is taken as F0 is A and B multiplied by F0, where F0, that is small f0, it is proof stress, and this proof stress is given as 0.7 times FUB, that is ultimate tensile stress in the bolt. So the proof load is actually the proof stress multiplied with the cross sectional area of the bolt at the level of the threads, and proof stress is 0.7 times FUB. Therefore proof load is F0, that is 0.7 FUB multiplied by A and B. So by knowing the value of the ultimate tensile strength of the bolt and the net cross section area of the bolt, you can determine the proof load. Then as per clause 10.3.3.1, the provision for long joints shall apply to friction grip connections also. So we have to use the clause 10.3.3.1 if the length of the joint is long, and we have to use it as per this clause only. Then we have the capacity after slipping given by clause 10.4.4, that is when the friction type bolts are designed not to slip only under service loads, the design capacity at ultimate loads may be calculated as per the bearing connection type. That's clause 10.3.2 and 10.3.3. That is when the slip is allowed at ultimate loads, the connection actually becomes a bearing type connection, because when the load applied on the joint is more than the frictional resistance provided by the joint, then there will be slip, and the bolt will finally bear against the connecting plates or the bearing area of the connecting plates. So it will be simply a bearing type connection, and we will have to design it accordingly. Then we have clause 10.4.5, that is tension resistance. A friction bolt subjected to a factor tension force of Tf shall satisfy Tf less or equal to Tdf, where TDF is the design tensile strength, that is, the tensile strength has to be more than the design force coming on the joint. And we have TDF, that is the design tensile strength, given by TNF over gamma MF. And we have TNF, that is nominal tensile strength of the friction type bolt, calculated as from clause 10.4.5. It is given as TNF is 0.9 times FUB multiplied by AN, and it has to be less or equal to FYB multiplied by ASB multiplied by gamma M1 divided by gamma N0, where FUB is ultimate tensile strength of the bolt, AN is the net tensile stress area of the bolt, ASB is the shank area of the bolt, that is area of cross-sectional area of the bolt at the level of shank, and we have gamma MF as partial safety factor, and FYB yield stress of the bolt. Gamma M0 is partial safety factor and its value is taken as 1.1, and this partial safety factor is for the resistance governed by yielding of the plates. And we have gamma M1, and that is the partial safety factor, and it is taken as 1.25, and it is based on the resistance governed by ultimate stress. And these values are actually given in table 5 of IS 800-2007. Then we have the combined shear and tension as per clause 10.4.6. Bolts in a connection for which slip in the serviceability limit state shall be limited, which are subjected to tension force T and shear force V, shall satisfy VSF over VDF whole square plus TF divided by TDF whole square less or equal to 1, where VSF is applied factored shear at design load, VDF is design shear strength, TF is externally applied factored tension at design load, and TDF is design tensile strength. Then as per clause 10.4.7, if there is a direct tension on the bolts, that is if we have a, for example, hanger type joint in which the bolts are subjected to direct tension, we have to reduce the tension in the, rather we have to add a force that is called prime force to the initial tension in the bolts. Generally, in connection is subjected to tensile forces, the flexibility of the connected parts leads to deformations that increase the tension in the pre-tensioned bolts. This additional tension is called as prime force. For example, consider a hanger connection as shown in figure. When the external tensile force or load is applied, the flexible flange or the flexible plate deforms. The flange is pulled by the tension, and the flanges at the ends are pressed against the connecting face. So we have in figure 2, when the plate actually detaches, when it is flexible, it detaches from the joint, so it actually introduces compressive forces, or it actually pushes the plate at the end, and due to this pre-compression there is actually the development of additional force that gets transferred to the bolt. So for example, we have a force 2 times TE applied to the joint, and the plate is flexible, so it deforms in this fashion, and there is actually the compressive force getting developed at the ends, and this because this plate pushes or presses against the flange, so there is a creation of some additional force at this point, and that compressive force tries to elongate or tries to introduce tension in the bolt. So the tension in the bolt will be TE, that is we have 2 TE, so TE will be subject to shear to this and TE will be sheared to this, and we have additional force Q that will add to the tension in the bolt, that is called as prying force, and it is denoted by Q. So this compressive force is called as the prying force, and it is developed at the ends of the flange or at the ends of the plate. Now in the tension connections, the magnitude of this prying force depends on the flexural capacity of the flange, or you may say on the thickness of the flange and or on the thickness of the stud. Further, it also depends on in other words, on the stiffness of the plates. That is, if the plates are stiff, the development of the prying force will be very small, because if the plates or if the flange and the plate are rigid and they are stiff, they may not deform, so there will not be any build-up of this prying force. So if the thickness is large, that is the plates are stiff, prying forces may be negligible. So in general, the bolt tension is increased by the prying forces or by the prying action to an extent of 0 to 20%. So we have to take into account the force, that is the prying force, in the case of joints, generally the hanger type joints, in which the bolts are subjected to direct tension in order to make the design safe. And this prying force is actually given in clause 10.4.7 of IS 800-2007, and it is denoted by Q. That is, Q is LV divided by 2LE, TE minus beta multiplied by neta F0 BE T4 over 27 multiplied by LE multiplied by LV square. So we have actually these different coefficients or different parameters given in the code, that is where LV is the distance from the bolt center line to the toe of the fillet weld or to half the root radius for a rolled section. As you can see, we have LV. This is the root or toe of the fillet weld. So from the center line of the bolt up to the toe of this weld, we have distance known as LV. And if the plates are not connected by fillet weld, if it is connected to the plate in the factory, that is, if it is factory made in such a fashion that it is rather a T section, then we have to take the value of LV from the center line of the bolt up to the root radius of that root, and we have LE, that is distance between prying force and bolt center line, and is the minimum of either the end distance or the value given by LE is 1.1 multiplied by T BF0 by Fy, and as you can see, it is the distance from the center line of the bolt to the end of the plate or up to the end distance of the bolt. So we have LE given by 1.1 T multiplied by B beta F0 by Fy, where beta is 2 for non-pretension bolt and it's 1 for pretension bolt. We have neta is 1.5. We have BE, that's effective width of the flange per pair of bolts, that is BE, that is given in the diagram as well. This is the effective width per pair of bolts, that is BE, and we have F0 is proof stress in the consistent units and T is the thickness of the end plate. So this was all in this lecture. In the next lecture we will actually design a friction type high strength friction type bolts. Thank you.